All right, so this is part 2 of section 2-5, and the first thing we're looking at is the linear factorization theorem. And that sounds like it's a big, complicated thing, but it's really not. It's exactly what we were just talking about. If I have some polynomial, and we'll say it's to the nth degree, so we could say to the 5th degree. And what the linear factorization theorem tells us is that means we're going to have n linear factors, which means that if I have like a 5th degree polynomial, I'll have 5 factors. That's not all the theorem is saying. So looking at our first example here, it says we have a 3rd degree polynomial, which tells us we're going to have 3 factors. And it says that we have real coefficients. And so it says we have one root is -3. One root, this should be a lowercase I here, like imaginary I. And we know that both of these terms here are roots. Now that tells us part of our answer. Now we know we have some coefficient a sub n out front. We know we have 3 factors, but they only told us 2. We have x plus 3 for the -3 here, and then we have x minus I for the I right here, but we're missing 1. Now, when they told us that I is a root, that's actually telling us that we have 2 roots. That's telling us that we have positive I and negative I, because any imaginary roots always come as pairs. So not only do we have x minus I, but we also have x plus I. So we do have 3 factors here. Now the only thing we're missing is the coefficient out front, but they told us this piece of information right here. And that's really just a coordinate. That's the coordinate 1, 8. So what we can do is we can plug in those values and solve for our leading coefficient out front. So plugging in 8 for our y value, and then a sub n, and then our x value is 1. So 1 plus 3, 1 minus I, and 1 plus I. So we can go ahead and multiply these things out. 1 plus 3 is 4, so I can divide both sides by 4. And I'm going to go ahead and FOIL this out right here. And when I do, I get 1 minus I squared. Now, I squared we know is -1. So I have 2 is equal to a sub n and 1 minus -1. Well, that's really a 2. So we have 2 equals a sub n times 2. And dividing both sides by 2, we get a sub n is equal to 1. And that means that our function is f of x equals 1 times x plus 3, x minus I, x plus I. And you can leave it just like that. All right, and we can go ahead and flip the page. And now we have what's called Descartes' rule of signs. And what that does is we're going to be looking at how many times our sign changes signs. So going from a positive term to a negative and vice versa. So we can see that the number of positive real zeros is the same as the number of sign changes of f of x. Okay? Or it could be less than that by a multiple of 2. And I'll show you what I mean in just a second. Now the number of negative real zeros is going to be equal to the number of sign changes of f of negative x, or again, reduced by 2. So the best way to really start to notice this is by doing an example. So that's what I'm going to do here. It says determine the possible number of positive and negative real zeros of this polynomial right here. So we're looking at how many times it's changing signs. So our first term is positive, and then the next term is negative. That's 1 sign change. Then our next term is positive. That's another sign change. So now we've got 2. Another sign change. Another sign change. So that's from positive to negative is 1, and then 2, and then 3, and then 4. So we have 4 sign changes. So what we're looking at for Descartes' rule of signs is looking at the positive real roots. And f of x has 4 sign changes. So we either have 4 real roots, so looking back up here, we either have 4 real roots, positive real roots, or it's going to reduce by 2. So we either have 4 positive real roots, 2 positive real roots, or 0 positive real roots. Now that's just talking about the positive real roots. We can also use Descartes' rule of signs to look at the negative real roots. And we want to use f of negative x. Okay. So first we need to find that. So f of negative x, well, plugging in negative x here, that's still x to the 4th power, minus 14, or that's going to be a positive 14x cubed, and plus 71x squared, and plus 154x plus 120. So looking at this, we have positive, 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 positive. There are no sign changes. For f of negative x. What that means is that there are 0 negative real roots. And about this point, you're probably thinking, why are we looking at this? What is this telling us? Why is this information useful to me? Everything we're doing up to this point is to gather as much information about these graphs as possible, because in a couple sections we're going to be graphing these functions without our calculators, and we need to be able to get as much information as possible looking at the equation here. So if I know how many positive real roots I have, that means that on this side of the x-axis I could either have 4 roots, or I could just have 2 of them, or I could have no real roots. And what this is telling me is that I definitely never cross the x-axis on this side. There are 0 negative real roots. So my graph never touches the x-axis on this side. Okay, so that's the information that we're gaining from these functions here. Just before we end this video, I'm going to add a little bit to the end here. If I have a function f of x with, let's say, 7 sign changes, then what that tells me is I either have 7 real roots, I could have 5 real roots, I could have 3 real roots, or I could have 1 real root, and these are positive real roots. So we're always reducing by 2, okay? So again, just one more example. If I have some f of x, let's say f of negative x gave me 8 sign changes. Then that means that I have 8 negative real roots, or I could have 6 negative real roots, or I could have 4 negative real roots, or 2 negative real roots, or 0 negative real roots. So that's the information that we're trying to get from Descartes' rule of signs. And that is the end of section 5.